Hi everyone, and welcome back to another AP Calculus video. Today we're going to introduce the concept of what we call an improper integral. And to understand what that is, let's take a look at a graph. Now, we know that if we're looking at a graph of a function, to find the area underneath, we would simply integrate from point A to point B. But suppose we take a look at some curves here, and I've got two curves all lined up here in Desmos, and they look very similar. And you'll notice that they have a horizontal asymptote at 0. And so if I wanted to find, for example, the area under the curve from, 1 to 5, I could do that by just integrating, and it would be easy, and the area would exist. But as I keep on going from 1 to 5, from 1 to 6, 1 to 10, 1 to 100, those areas exist. But what happens when that limit approaches infinity? What happens when I go way far out? And I want to know, does the area underneath this curve from 1 to infinity exist? Is it an infinite area? Or is it something else? So my answer to you is that sometimes it's infinite, but sometimes it's not. And we're going to take a look at this, and we're going to see kind of why that is and what makes it so interesting. And I'm going to tell you right now that one of these curves has an infinite area from 1 to infinity, and one of the curves does not. One of the curves has what we call a finite or a discrete area that we can find. So the idea here is, remember, when we talk about finding the area, I want you to kind of remember what's happening. Finding the area under a curve, we slice it up into little rectangles, and we're adding together these rectangles. That was kind of the basis of Newton when he created the integral, and Leibniz for that matter, and Riemann, and they all came together and they said, we're just going to slice it up into little rectangles. And the width of the rectangles gets infinitely small. Well, if we take the area of those rectangles and we add them together, what we end up with is what we call a series. And when we have a series of numbers or a series of terms, remember we introduced the concept of a sequence earlier in this unit. A sequence is a list of numbers. We're going to be approaching what's called a series. And a series of numbers is what we get when we add those sequences together. And there are some series that actually have a sum, and we can add them up, and from 1 to infinity, they actually add up to something. And so, for example, if I try to add up all the terms in a series, suppose I have an integral where the first rectangle has an area of 1, the second rectangle has an area of 1/2, and I keep cutting them in half and in half and in half. And what we end up with is we get this infinite geometric series. And you're going to find that this infinite geometric series, if I add it up, if I continue to add up these terms, this infinite geometric series actually adds up to 2. And you can type it into your calculator, and it's kind of a neat little thing where if you just keep going 1 plus 1/2 plus 0.25 plus 0.125 plus, and then you just keep going, 1 divided by 16 plus 1 divided by 32 plus 1 divided by 64. You're going to get that in your calculator. It'll start, as you add the next term, it's getting closer and closer to 2. And so we say that when we have a certain type of series, sometimes those numbers will add up to a set value. Even though there's an infinite number of terms, they'll add up to something, right? And it just has to do with the behavior of the function. And this is called a geometric sequence or a geometric series. When we add them together, we just change the word to series when there's plus signs. And an infinite geometric series will add up to something, provided that the terms are getting smaller. If the terms are getting bigger, well then it adds up to infinity, and that's not that means it doesn't do what we say. It doesn't converge, it diverges. So it is possible to have a list of numbers that adds up to a certain value. And when I look at the area, if I remember that the area is just a bunch of little rectangles, well, what if the rectangles produce a pattern that actually adds up to something? And that's what we're going to talk about here. That's the whole point of exploring what's going to happen here. And this is going to lead us into the next unit where we're actually going to look at these series, and we're going to say, do the series add up to things? And in a geometric series, we're here, remember our common ratio is 1/2, so we're cutting in half each time, or multiplying by 1/2. If that common ratio is less than 1, in other words, we're cutting in half, then my geometric series is going to converge to a number. It's going to add up to something if it's infinite. The same situation can be true if we exhibit a pattern where the rectangles form this geometric series. Well, then we're going to converge. We're going to have a concrete finite area under an infinitely large, curve that goes to infinity. It's pretty cool. But when we have a function that doesn't have that behavior, well, then it's not going to converge. It's not going to add up to anything. The area will remain infinite. So, depending on the behavior of the function, we could have either case. So let's take a look. How do we deal with this? Well, when we're evaluating an integral, when we're dealing with an infinite space, if one of our limits is infinity, then we call it an improper integral. You can't have a limit of infinity. And the way that we deal with these, they're either going to, like I said, converge to an answer. In other words, the rectangles add up to something. Or they're going to diverge and there's going to be an infinite area underneath. That could happen too. To evaluate them, what we do is we have to turn them into a proper integral. And the way that we do that is we express it as a limit. And so you can see here that when I have the limit, or when I have an integral where one of my limits is an infinity, then what I do is I say I'm going to replace that infinity with a b or some sort of constant, some other variable, and then I rewrite it as the limit as b is approaching infinity. So essentially that's what I'm doing, is I'm rewriting that limit as, rewriting that integral limit of integration as a limit as that value approaches infinity. So when I have a situation where maybe it's possible that I would evaluate a function from negative infinity, so positive infinity, well then I would have to break it up and express it as two integrals. So I would split it and I'd say, well, from negative infinity to something. Oftentimes we'll use 0 because 0 is a really great number. So oftentimes we'll use 0 here and 0 here. Whatever number you choose to use, though, you're going to want to make sure that you use it both places. And then we express it as two improper integrals. We say the limit as one of the limits is approaching negative infinity and the other limit is approaching positive infinity. So essentially it is possible that both limits could be infinities and we would have two improper integrals to evaluate as limits. So let's take a look. And remember, as always, when I'm dealing with limits, I want to be aware of my indeterminate forms as they do tend to show up. So this time though, I'm going to be looking out for this one right here. That's a big indeterminate form. Remember, not all infinities are equal. Some functions approach infinity faster than the others. So let's try it out. Let's see what's going to happen. So the first thing I'm going to do is we'll call this one number 1. Let's just do number 1. The limit as b approaches infinity from 1 to b. The first thing I do is this. Okay. Now I'm going to do my antiderivative, just like always. So 1 over x, the antiderivative is the natural log of x. And I'm going to go from 1 to b, the limit as b approaches infinity. Okay, well now it's an antiderivative. I'm going to use that fundamental theorem of calculus. So here we go. I'm going to keep my limit notation. And I'm going to do this, the natural log of b minus the natural log of 1. Okay, well the natural log of 1 is 0. Okay. So really this is just the limit as b approaches infinity of the natural log of b. b is positive, so I really don't need my bars there. Well, you guys, that's just infinity. This diverges. So let's talk about what this means, diverge or converge. We use the word converge when it works out to a number. It converges. If we ever get infinity or a non-existent thing, then we say it diverges. That's really all we do. Converging means that the answer exists. Diverging means that it's an infinite area. We can't find it. That's really all it means. Let's take a look at the other one. And if you want to pause the video and try it on your own, I would encourage you to do that. Otherwise, work it out here with me. So first step, I'm going to rewrite it as a limit. The limit as b approaches infinity from 1 to b. Now I'm going to do my antiderivative. So this is x to the negative 2. So the antiderivative would be x to the negative 1 with a negative. 1 to b. So then limit as b approaches infinity of negative 1 over b minus negative 1 over 1 plus plus. Oh, well, as b approaches infinity, this is 0, and this is just 1, so guess what? This integral converges to 1. Hooray! So, like I said, sometimes you'll get an area, and sometimes it'll diverge to infinity. Here we converge to 1. So the area under the curve from 1 to infinity, those little rectangles must form some sort of geometric series or something that converges to 1, and it adds up to something. So just remember, sometimes you have a convergent integral that adds up to something, and sometimes you don't. Let's keep going. Let's try another one. Here we have an integral where it goes from negative infinity to infinity. So the first thing I'm going to do here is I'm just going to split it up, and I'm going to say, okay, well, let's say from negative infinity to 0, and then from 0 to positive infinity. So it's nice and simple. I have two improper integrals that I'm going to evaluate. So it's just twice the work, not a big deal. So the first thing I'm going to do is I'm going to rewrite them as limits. So the limit as, I'm going to use a. I'm going to use a and b. Plus the limit, and then we'll use b for the positive infinity. Just that way we can tell a difference. Now, this one, the antiderivative, this is a good review of integration. This is actually the inverse tangent. So if you were looking at your formula sheet, hopefully you should recognize this as arctan or inverse tangent. So let's go ahead and write this out. The limit as a approaches negative infinity, and this would be tan inverse of x from a to 0. And then b approaches positive infinity, tan inverse of x from 0 to b. So now I'm going to write it out. The limit as a approaches negative infinity, and I'm going to have tan inverse of 0 minus tan inverse of a plus the limit as b approaches infinity, tan inverse b minus tan inverse of 0. Oh goodness, how do I find tan inverse of something without a calculator? Well, this says there's some angle. Whenever I have tan inverse, really this means there's some angle, tangent of theta, where it's equal to 0. So what's the theta? Well, let's think about this. We're going to be using principal values. So which value has a tangent of 0? Well, that's sine over cosine, so the sine must be 0. So it must be 0. So the theta must be 0. So this is 0 and this is 0. So it's saying what angle has a tangent of 0? 0 and pi. But since we're dealing with principal values usually, we're going to go with 0. So then we have to deal with this limit here. As the limit, this ends up being negative tan inverse of a, this limit, plus the limit of tan inverse b. So let's go ahead and drop the tan inverse to 0. Now, what is this? What's happening? Well, we have to kind of remember what tan inverse looks like. So remember, a tangent curve looks like this. So this is tan, right? It's got all these things and kind of goes like this over and over again, right? Well, tan inverse takes that. Remember, we're revolving it around or reflecting it about the line y equals x. So tan inverse essentially ends up looking like this. Okay, and Here this is negative pi over 2, this is positive pi over 2. So the horizontal asymptotes kind of look like this. So essentially it just kind of gets flipped on its side. So what's happening as I'm approaching positive and negative infinity? Well, as we're approaching positive infinity, oh look, my function's approaching pi over 2. As we're approaching negative infinity, oh look, I'm approaching negative pi over 2. So it works, but you have to know what the function looks like in terms of its graph. So approaching negative infinity, this is going to be negative pi over 2. And then approaching positive infinity, it's going to be pi over 2. Negative negative turns to a plus. Oh look, this integral adds up to pi. So knowing what your functions look like can be helpful in certain situations. So let's keep going. Let's review some more integration techniques. Let's try this one here. So the first thing you want to do, and if you'd like to pause the video, I'm going to give you a hint. This is a good review of partial fractions. So see if you want to pause the video and give it a try, see if it comes back to you. Otherwise, stick with me. Remember, your first step is to write it as a limit. You must express it as a limit to get credit on the AP exam on a free response. So I'm going to keep that limit notation. And now I'm actually going to go over here and I'm going to do my partial fraction work over here. Factor that bottom. So then this becomes a over x plus 3 plus b over x plus 1. So when I multiply by what's missing, x plus 1, x plus 1, x plus 3, x plus 3, I get this. My numerator must be the same. So a times x plus 1 plus b times x plus 3 must equal 2. So now I'm going to use my little trick. I'm going to say let x equal negative 1. That gives me a 0 for the a term. I get 2b equals 2, so b must be 1. And then I say let x equal negative 3. That cancels out the b term. And I get negative 2a equals 2, so a must be negative 1. So now I'm going to come back over here. A is going to be negative 1. B is going to be positive 1. So I figured out what a and b are for my partial fractions. And now I'm going to go back over and I'm going to do my integration and find my antiderivatives, which are going to involve natural logs. So let's rewrite it a little bit here. So I'm going to say 0 to b, I'm going to have negative 1 over x plus 3 plus 1 over x plus 1. So this is going to be the limit as b approaches infinity. I'm going to have negative ln x plus 3 plus ln x plus 1, 0 to b. Now before I do any more, here's what's going to happen. When I put in 0, I'm going to get some numbers. But I'm going to end up having like infinity plus infinity or infinity minus infinity. That's going to be a problem for me because I'm going to have the natural log of 1, the natural log of 3, plus some infinities, and it's not going to be great. And remember, infinity minus infinity, we don't know which one's faster. So if one infinity is really large or large by a certain amount, infinity minus infinity could actually be a concrete number. So that's why when we get infinity minus infinity, it's one of those indeterminate forms that we talked about. So this infinity minus infinity, this infinity here could be a lot larger than the other infinity. And when you subtract them, maybe they actually work out to something. So infinity minus infinity is an indeterminate form, which means we need to take some care and do a little bit more with this. So I'm going to come back down here and I'm going to actually switch these two terms, because when I have natural logs that are subtracted, what I can do is I can rewrite them as a single natural log. So I'm going to rewrite it as ln x plus 1 minus ln x plus 3. That gives me this, x plus 1 over x plus 3. Oh, from 0 to b. All right, so now I'm ready to plug some things in. So I'm going to go ahead and limit as b approaches infinity. I'm going to have the natural log of b plus 1 over b plus 3 minus the natural log of 1/3, because I'm going to plug in 0. Okay, here we go. Now, I'm going to evaluate as b approaches infinity. Now, here's the cool part. When I put infinity into this little spot, I end up getting infinity over infinity, which, you guys, is an indeterminate form. So I'm going to kind of like L'Hopital my way through the middle here, because really one of the things I want you to understand is that when you have a function inside of another function, you can evaluate the inner function's limit and use that to find the outer function's limit. So really what we're doing is we're saying, well, what is the limit as b approaches infinity of this? Well, it's 1 when we do L'Hopital's rule, or if we use, simplifying or an end behavior model, it's just 1. So really, the limit as b approaches infinity of the natural log of this is the natural log of 1. It's terrible handwriting. Well, what's the natural log of 1? Well, the natural log of 1 is 0. So this turns into 0. By evaluating the inner function and its limit, we're able to evaluate the whole function. So we get 0 minus the natural log of 1/3, which that's not too bad, so it's negative ln 1/3, or natural log of 3. Remember that negative 1 turns into a power, so you get 1/3 to the negative 1 power, which flips your fraction. So either one of these is a totally, you could do that too. So either one is fine. But just my warning to you is this: when you have natural logs and you have infinity plus infinity, well, infinity plus infinity is infinity, but when you have, infinity minus infinity, like we had here, you can't do subtraction with infinity. You can add infinities, they'll add up to infinity, that's pretty obvious, but you can't subtract, because remember, it all comes down to infinity being a concept, not a number, and one infinity might always be larger than another infinity. So when we're dealing with these types of functions, we need to be using all of our tools for integration in addition to our concepts of evaluating limits. So these are big problems. Let's do one more here, and just to kind of give us a feel for how it goes. So here we go. This is a good review of integration by parts, or tabular integration. I'm going to go ahead and probably use some tabular integration, but integration by parts, remember, it's u dv uv minus v du. So there's my integration by parts. We always let u be determined by Lipit. So there's a quick little snapshot review. So let's see it come down and go into play here. First things first, rewrite it as a limit. All right, now we're going to integrate. And I'm going to let u be the polynomial, and I'm going to let dv equal e to the negative x. So that means using tabular integration, well, I guess I can use integration by parts. It doesn't really matter. So here we go. This is going to be the limit as b approaches infinity. And I'm going to have u times v, so that's negative x e to the negative x, minus the integral from 1 to b of v du. So I'm going to integrate one more time. So this integral just becomes e to the negative x. All right, now I don't like negative exponents. So anytime we're evaluating limits, we want to get rid of negative exponents. So get rid of / simplify negative exponents. So what I mean by that is this. This is going to be the limit as b approaches infinity of negative x e to the x minus 1 over e to the x. Now the reason why we do that is because we're going to be thinking about x approaching infinity here in just a moment. And when it's in the bottom, it's very clear to see that especially that second term is going to go to 0. So here we go. We're gonna go ahead and plug some things in. So we're going to have the limit as b approaches infinity of negative b over e to the b minus 1 over e to the b minus, I'm going to go ahead and plug in 1, negative 1 over e minus 1 over e. So now I'm going to evaluate the limits. So as b approaches infinity, well, this guy goes to 0. But this guy, I need to L'Hopital my way through this. So L'Hopital this. And for these types of problems, I'm just going to kind of go off to the side and evaluate it. I'm going to do the limit as b approaches infinity. I'll have negative 1 over e to the b. Well, that's going to go to 0 as well. So for these types of problems, being formal with your L'Hopital's rule isn't necessary. On a free response for your AP exam, it is necessary. But here, since we're just trying to get to the bottom of this and evaluate this, I'm going to go ahead and just say it goes to 0. So 0 minus 0, that's just 0. So here we go, minus, so plus 1 over e plus 1 over e, that's 2 over e. And that's my answer. So evaluating these gets really complicated. We need to be confident in our integration techniques. We need to be confident in our limit techniques. We need to be confident with our L'Hopital's rule. There's a lot of pieces that go into solving these problems. And the more of them you do, the better you are going to get. This is a complex one. The other type that is complex is the natural log problem with the subtraction. Remember to be aware of those indeterminate forms, 0 over 0, infinity over infinity, infinity minus infinity. You have to algebra your way through those. So keep at it, keep practicing. You can do this. You've got this.